Our discussion on the overview of experimental stress analysis, and in the last class I said that when you say stress analysis in the complete sense, it means determination of 6 stress components, 6 strain components and 3 displacement components. However, I said determining all these 15 quantities may be a luxury. From a design point of view, you may not need a full complete solution. So, depending on the problem on hand, you may want to find out only the relevant parameters and then use it for your design. And to do the stress analysis, we have also seen that you could do it by analytical methods, numerical methods or by experimental means. And in complex problem situations, we may want to use more than one technique so that we get the problem on hand solved satisfactorily. And if you get into analytical methods, what we find is you get a conceptual understanding on the nature of stress fields. For example, can I have one of the students come here and then show this model? And one of the simplest problem that is first taken in course in strength of materials is a slender bar pulled in tension, and in this zone away from the grips, you all know that stress is constant and that is given by P by A. And what I emphasized yesterday was you evaluate only a component and you have to learn that you have to put it in a 3 by 3 matrix and put the relevant zeros and understand this as a stress tensor, not just as a stress component. And a problem of this nature, you have ready made solution without solving differential equations from strength of materials. The moment you take another problem for the same plate, if you introduce a hole, it is just not possible to solve from strength of materials, because the moment I put a hole, plane sections do not remain plane before and after loading. Before and after loading, plane sections do not remain same. So, your assumption of strength of materials approach will not help you to solve. And if you ask the question, can this at least be solved by theory of elasticity, which is also not possible, because the size of the hole is comparable to the width of the specimen. However, you can still attempt to solve by theory of elasticity if the hole size is very small like this. For the same width of the member, if the hole is very small, though physically this is a finite body, from a mathematical sense this could be considered as at infinite distance away, and you could invoke theory of elasticity solution and then get a closed form expression. So, the size of the hole is very small compared to this. Suppose I have a complex object, what do I do? I have a complex object like a spanner, and this is a down to earth object, you use it at many of your day to day activities. Do you get a solution from analytical methods? You do not get this. It is such a routinely used specimen, a tool. If you want to solve it from your course in strength of materials, it is just not possible to solve. And let it tighten a nut, and what you find here, I have this spanner and I have the nut here, and when I start tightening the nut, obviously you will find stresses are developed. Do you see the stresses here? You do not see the stresses here. And what you can say from strength of materials, because this is constrained here and you are applying a load here, some sort of a bending takes place in the member, and since you all know something about stress concentration, you could at best say there will be stress concentration in this zone and this is the load application point. So, certain general observations you could make from your knowledge of strength of materials. Because the geometry is complex, you cannot solve it by strength of materials, even theory of elasticity will not help, The only recourse that what you can do is you have to do it only from a numerical technique or an experimental method. And what we are going to see is we are going to introduce a new concept that optical methods work as optical computers. And this is what we had seen physically. A nut was tightened by a spanner, and it is natural to expect that stresses would be developed in the components, and you do not see them. The difference what I have shown in the previous live exercise and what you see on the screen right now, the spanner is made of epoxy and nut is also made of epoxy. I have a reason for it, because I have an interest to show even the stresses as they develop when the nut is tightened by the spanner. So, what we find is a very simple problem, down to earth problem. You do not have solution from strength of materials after full course on strength of materials. You can only at best conjecture what could be the stresses, not the actual magnitudes. And what you have is, why I have taken epoxy is the spanner and the nut are made of epoxy, and it possesses an unique property of stress induced by refringence. See, earlier I have told you that each of the experimental technique utilize a particular physical principle which is exploited to reveal a particular kind of information. It will not give all the stress components, all the displacement components, all the strain components. And here what we have done is, we have taken a spanner and nut which is made of epoxy, and it possesses a unique property of stress induced by refringence. And what I do now is, I introduce appropriate optics and view the same combination with the optics. Optics is not shown here in the screen, but you will see the effect of optics seen on the image. And what you have here is, as I change the load, as I keep increasing it, you find that more and more colors are emerging and it is seen. So, what it shows is, whatever the colors that you see are a function of the load applied. And I would like you to make a sketch of this in a reasonable manner, at least for the spanner. Forget about the nut, at least for the spanner you make a reasonable sketch of the spanner. And you should thank the nature, these are not artificial colors. It reveals the stress information in the form of such rich colors. The colors are very nice, and normally when you go for a computer plot, you usually plot to indicate what is of a high value as red and low value as blue, and you have a grayscale suitable for different application. But here the colors are seen naturally, and nature wants to reveal the stresses in colors to enthuse the experimental mechanics person to conduct the experiment. And I would like a reasonable sketch of it, capturing the salient features. Okay. And what you have here is, you have stress concentration, this is the load contact point, and you have stress concentration here, and you have the fringes developed on the edges, and you have seen very clearly, that all these colors have emerged as a function of what you have applied as load. And for your benefit, I will repeat it again. So, when I have the least load, it is like this. As the load is increased in stages, you find the fringes are formed, and we call these as fringes. And what you get here, I get first information I get is I get this over the entire spanner, I get information. So, I get a whole field information from an experiment, a whole field information from an experiment. And what I have here is the results in the form of contours have been obtained, and I have got it without solving a differential equation, because what is the effort that I have done is I have to make the model of the spanner as well as the nut, and then put it in appropriate optics and reveal the pattern. If I had to do a similar exercise as a numerical approach, what I will have to do is I will have to formulate the problem as set of differential equations, solve it either in closed form or at least in the form of approximate approach, then replot, go to a computer, use a plotting software and replot the values, then I will get these contours. So, in that sense what I could say is that optics has done the job for you. So, I could call this as optical methods working as optical computers. The effort that you will have to do is you have to make the model, there is no escape, there is some price you have to pay for it. In a case of numerical method, you have to pay a price in formulating the problem. In the experimental method, you have to pay a price in fabricating the model. Now, what is important is I have seen these rich contours, and what these contours are. How do I know what these contours represent? So, here only you have to look at what is the physics behind the problem. So, physics is very important in understanding and interpreting the results given by an experimental technique. If you do not know the physics, you will not be able to interpret the fringe patterns, and that is what is summarized here. And what you have is one needs to know what physical principle does an experiment exploit to reveal the physical information. In fact, the purpose of this course is get into the physics of the problem and understand for yourself completely that this physics is exploited, and what I see is this is the contour. But what I will do now is, you take my word for granted at this stage of the course, and in the present example the contours observed are isochromatics depicting contours of principal stress difference. And for you to understand this, we have to develop crystal optics. The technique that is used is photoelasticity, and as I said, which exploits stress induced by refringence to reveal the stress information. That is why I have taken a specimen which behaves like a crystal when it is loaded, that is what the epoxy that has a phenomenon of stress induced by refringence, and because stress has induced the changes in the optics. So, by analyzing the optics information, it is possible for you to relate the effect of optics in terms of stress patterns. So, that is what we have done in this simple exercise, and if you want to have a complete understanding, you have to have a basic understanding of what is crystal optics. That also we will develop later in the part of the course. Currently, the interest is to focus, when you look at any experimental technique, you need to understand the physics behind it, and physics would be different for different techniques. Only if you know the physics, you would be able to interpret. Getting colored contours, the two colored contours is very nice, but experiment does not stop there. After getting the colored contours, you should know how to interpret it. The interpretation is possible only when you have understanding of physics, and many instances interpretation itself will be very challenging, and this is where people would like to take the assistance of automated data acquisition and processing methodologies, where they would like to minimize the interaction of the person conducting the experiment. And you have to understand, you will be surprised, many of you have done in your physics course, you would have done an experiment on finding out the refractive index of a glass, and you would have just got a number, and you would have thought, like in the case of introducing strength of materials, you take a slender member and then pull it, and then you find out stress introduced is P by A, you think that it is a scalar, because you are only looking at the component where you are looking at the value, you are not looking at totality of the stress at a point of interest. Similarly, you tend to think that refractive index is also a scalar. In fact, it is not so. Refractive index is also has direction dependence, and it is a tensor of rank 2. Stress is also a tensor of rank 2. So, whatever modification on the refractive index, if you are able to capture it by optics, you could relate that to stresses. And if you look at, this was developed way back in 1816 or so, and Brewster did first set of experiments. So, this is what I would like to emphasize again. We do not solve a differential equation, from that point of view it is advantageous, but the limitation of an experimental technique, it cannot reveal all the 6 stress components, it cannot reveal all the 6 strain components, it cannot reveal all the 3 displacement components. In this particular experiment, we have been able to get only sigma 1 minus sigma 2. So, to start with, it will appear, oh, I do an experiment, I do not get everything under the sun, it may look like a limitation, but this is not a serious limitation, and this is where, as an engineer you have to apply your engineering acumen to choose an appropriate experimental technique or a combination of them to solve a problem on hand. This is where the engineering acumen is required, and that comes only by practice. See, complicating a problem is very simple, simplifying a given problem on hand is the most difficult aspect, and that comes only by experience. Sometimes very simple methods can solve a complex problem. So, you should be open to new ideas, and you should know what kind of facilities that you have. Based on that, based on the time constraint, you decide an appropriate combination of techniques to solve it. And another word of caution I would like to say, what I would like to say is, see, as an experimental person, the person may be interested in developing as much as possible from a given experimental technique. So, in the process we may do more than what is really required, and then try to say you use complicated steps to extract maximum from a given experiment, because when a new methodology is proposed, he would like to get that methodology established, and he would like to show that it can be used for a variety of problems. But from a user point of view, a particular feature of an experimental technique may be more appropriate, and that is enough for you to solve without getting into the ramifications of using that with a constraint. So, as an user, you should also use only those aspects of an experimental technique which are appropriate for your problem on hand. And that is what I said, to do this one needs to know what an experimental technique can give and what is the physical principle it is based upon, and these are discussed, these will be discussed as we go by.